Here is a giant bobbin, made of a spool and a string. If you pass a rod through the hole of the spool, fix it in place, rest both ends of the rod on two boxes, and gently pull the string toward yourself. Making sure there's no slipping between the rod and the boxes, the spool rotates and rolls away from you. That part feels intuitive, right? Now, let's try something slightly different. Instead of the rod touching the boxes, place the spool itself directly on top of a box and pull the string in exactly the same way. Again, making sure there's no slipping between the spool and the surface. You're still pulling the string toward yourself, just like before. So, it feels like the spool should roll away from you. But at the same time, since you're pulling toward yourself, it also feels like it might roll toward you instead. I could save the answer until the very end, but I'll just tell you now. It does, in fact, roll toward you. Did you guess right? If that sounds hard to believe, try it yourself with a sewing kit spool. It works surprisingly well. This is one of those ordinary physical phenomena hidden in everyday life. The kind that makes you think, who even cares about this? But once you've started thinking about it, not knowing why it behaves the way it does leaves you feeling strangely unsettled. At least, that's how it feels to me. Hopefully, we feel the same here. The goal of this video is very simple: to build an intuitive understanding of why a spool placed on a surface rolls in a particular direction. And along the way, I hope we can enjoy the kind of beautiful patterns that emerge when we look at even the most mundane scenes through the lens of physics. To make things easier to see, let's simplify the situation a bit. Instead of thinking in full 3 dimensions, we'll look at what happens from the side when the string is pulled. In one case, the rod fixed to the spool touches the boxes. In the other, it's the circular disc of the spool itself that touches the box. The key difference between these two situations is the geometric relationship between the point where the object touches the surface and the point where the pulling force is applied. In the top case, the rod is what touches the boxes. In the bottom case, it's the spool itself that sits directly on the box. So, here's the question I want you to keep in mind. Let's assume you just pull the string and the spool starts rolling. At this very instant, which point is not moving? Let me show both cases with several points on the disc to easily see rotation. Watch carefully and try to spot which point isn't moving. Do you see it? Or does it feel like every point was moving? Well, that reaction is completely fair. Just watching a rolling disc, it's honestly hard to tell what anyone could even mean by a point that isn't moving. So, let's make things a little more explicit. This time, I'll visualize the velocity of each point. I want you to look at these velocities and find when they become 0. How about now? Let me do the same thing for the bottom spool. Simply by visualizing the velocities, it almost feels, at least to me, like you've gained a special ability to see what's really going on. That green point is the heart of this entire question. It's doing something very special. In fact, it even has a name: the instantaneous center of rotation. At any given instant, this is the point on a rigid body whose velocity is exactly 0. A rigid body is just a physics term for an object that doesn't change its form, like a hard plate. You might wonder why it's called instantaneous, and it really does mean exactly that. It can change from moment to moment. In fact, in most cases, there's no single point that serves as the center of rotation at all times. From here on, let's explore how the positions of different points on a rigid body are related to one another, and how those relationships connect to the instantaneous center of rotation. Since it's hard to tell whether a circle is rotating just by looking at it, let's switch to a rectangular shape instead. Okay, let's consider the motion of a rectangular plate. Let's add a point P at the center of the rectangle, and attach a coordinate frame to it. Then, duplicate the coordinate frame at the corner of the rectangle. Whether a point is at the center of the rigid body or at its edge, the angle, angular velocity, and angular acceleration are the same. If we know how point P moves and how the rigid body rotates, we can calculate how another point Q on the same rigid body moves. These relationships are captured by the rigid body equations. First, it's the relation of the position vectors. Then, the relation of the velocity vectors, and finally, the relation of the acceleration vectors. Points P and Q are 2 locations on the rigid body. The vectors omega represent the rigid body's angular velocity, and alpha represent the angular acceleration. If you're already very comfortable with vectors, you might want to skip ahead about a minute and come back when we return to these equations. If vectors feel a bit rusty, let's take a moment to review just the bare minimum we'll need. A vector is an arrow that has both length and direction. As long as two vectors have the same length and direction, they are considered the same vector. Vectors have addition and scalar multiplication. Vector addition can be visualized by connecting the tail of one arrow to the tip of another. Scalar multiplication keeps the direction the same while stretching or shrinking the magnitude. And there is cross product. The cross product of two vectors is a vector that is perpendicular to both vectors and given by the right-hand rule. The magnitude of the cross product is given by the area of the parallelogram, which is given by AB sine theta. Now let's return to the rigid body equations we introduced earlier. You can see that they are written using only vector addition and cross products. For the case of two-dimensional rotation, let us focus on what the cross products of these vectors actually produce. In two-dimensional motion, the angular velocity vector and the angular acceleration vector always point along the axis of rotation, that is, perpendicular to the plane in which the motion occurs. If we return briefly to three dimensions, this is easy to visualize. The angular velocity and acceleration faces outward from the plane of rotation. Meanwhile, for the planar rotation, the vector RPQ always lies within the plane. As a result, the cross product omega or alpha cross RPQ yields a vector whose direction is obtained by rotating RPQ by 90 degrees counterclockwise, and whose magnitude is multiplied by omega. Using this identity, we will gradually massage the equations into a more convenient form. When we apply it once, some unusual symbols appear on top of the RPQ vectors. Technically not standard in mathematics, but let's agree to use them here as a convenient way to represent a 90-degree rotation. At this point, note also that the vector symbols above omega and alpha disappear, and they become scalars. There is still one more cross product left, so let's push it a bit further. Now, you might think, there are too many arrows here, it's hard to read. But remember that applying a 90-degree rotation twice results in a 180-degree rotation, which simply reverses the direction of the vector. In other words, it becomes negative RPQ. Now, let's look at some specific motions. First, suppose point P moves straight sideways without any rotation. In that case, omega equals 0, alpha equals 0, and points P and Q move with exactly the same velocity. If P follows a figure-8 trajectory, acceleration appears, but as long as the rectangle itself isn't rotating, every point on it still shares the same velocity and acceleration. From here on, we'll only consider cases where angular velocity is constant. If we allowed angular acceleration, things would get even more interesting, but there's already plenty to explore. Next, let's keep point P fixed and rotate the rectangle about P with a constant angular velocity. Although the angular velocity is the same for every point, the positions of those points relative to P differ. So let's pause the motion and focus on how the vectors change as point Q moves closer to or farther from P. The closer Q is to P, the smaller its velocity and acceleration become. The farther it is, the larger those values grow. Now let's combine translation and rotation while moving point P at the same time. If we slide the object to the right while rotating it, you can see that the velocity of point Q differs depending on whether Q is on the upper side or the lower side. If you try to think about why this happens, the answer may not come immediately, but the reason is that the motion is determined by the same equations. Whether P traces a figure-8 path or the object rotates, the resulting motion of Q follows the same underlying rule. At this point, just watching the motion alone might be enough to make some of you feel dizzy. So let's pause and break it down more carefully. Point P contributes a translational velocity. So this component of point Q is the same as the velocity of point P. Rotation about P contributes another velocity. So this component of point Q is omega times the position vector from P to Q, rotated 90 degrees. And the velocity of Q is simply the vector sum of these two components. By adding the second vector's tail to the first vector's tip, we get the total velocity of point Q. Next, we'll let point P follow a few different kinds of motion, while keeping the angular velocity the same. Let's arrange the animations in a grid. In the left column, you see different motions of point P's where the rectangles do not rotate, and all the points in one rectangle move the same way. In the middle column, P's are stationary, while the rectangles rotate around P's. In the right column, you see the combination of the two motions, where the position of P's changes and the rectangles rotate. It is not a main focus of the video, but I cannot help but find the paths that point Q's trace beautiful, aren't they? Anyway, let me just play the animation for a while. Now, you might have already forgotten the original question we had. So let's remind ourselves. The question was, which direction does the spool roll and how does it relate to what we have seen so far? At this point, many of you might know why I brought up a rather peculiar concept called the instantaneous center of rotation. Again, if a point on a rigid body has zero velocity at a given instant, that point is the instantaneous center of rotation. In our rectangular examples we saw, this is point I. Instantaneous center of rotation is found by solving the equation with zero velocity at a given instant. This point can be found by rotating the velocity of P by 90 degrees counterclockwise and dividing by the angular velocity. If omega is negative, we need to flip the sign of the velocity. Interestingly, the instantaneous center of rotation doesn't always lie inside the object. Now, let's return to the spool. Where is the instantaneous center of rotation in this situation? The answer is, because the spool is rolling without slipping, at each moment, the contact point of the spool and the surface has zero velocity, which makes it the instantaneous center of rotation. And what ultimately determines the direction in which the spool rotates is the geometric relationship between a contact point and the point where the force from the string is applied. When the rod rests on the box, that geometry causes the spool to rotate opposite to the pulling direction. When the spool itself touches the box, the geometry flips, and the spool rotates in the same direction as the pull. This small geometric detail ends up deciding everything. Once you see it this way, it's hard to unsee. The idea for the visualizations was largely inspired by Matthew West's website. It's a really well-crafted resource, and I highly recommend checking it out. If you found this video interesting, please give it a like, and share it with someone who might enjoy it as well. I'll see you next time.